In the first session of the tutorial, we said the first step in the GM over ID technique is to characterize the MOSFETs, that is to characterize the NMOS and PMOS and generate uh, some typical plot that we can use for the design. So first of all, we are characterizing a NMOS of 180 nanometer, and let us make the circuit setup for the characterization. So I'm naming as NMOS Cara. Okay, and I'm inserting the 180 nanometer NMOS, and here is our NMOS. And its width and length I am giving as variable. Width I am giving as width itself, and length as length itself. Okay, now we need DC sources. So since it's a 180 nanometer technology, the supply voltage, that is VDD, will be 1.8 volt, and for characterization, the VDS I am giving half of VDD, that is 0.9 volt. So that will be a reasonable VDS for our characterization, and we will sweep the BGS to get different parameters. So this will be our VGS, and let the DC voltage as it is, and we need ground now. Now connect them together. The body also, the body, that is the bulk, I am connecting to ground. And this is the basic setup for the characterization. Now we can start the ADEL. In the ADEL, we can load the variable that we give, that is the length and the width. So the length, I am giving minimum length as the 180 nanometer, and the width I am giving a reasonably high width like 5 micrometer for the characterization. During the characterization, we will change these parameters. We will change the length and we will keep the width almost the same, because all the parameters that we are characterizing today is almost independent of the width. So we will keep the width as 5 micrometer itself, and the length we will change. Oh, sorry, there's a spelling mistake in the length. So let's correct it. Length, okay. P 180 nanometer, and let us choose the DC sweep, and in DC sweep we have to sweep the VGS. So I am selecting the component, this DC voltage as a sweeping variable, and I want to sweep this from 0.2 volt to 1 volt, and it will give a reasonable VGS value. in any analog design. So, and let us run the simulation. And we didn't specify how many steps we have to do in the sweeping. So I'm specifying that steps as number of steps I need only, okay, let us say 50 steps, and I want to float the current. Okay, let us float the current output to be floated. So the drain current I am floating now. Second save, run the simulation. Now we are sweeping the VGS and we are plotting the drain current ID. So we should get a graph with VGS in the x-axis and ID in the y-axis. So this is the same graph that we expected, and we are very familiar with this graph. But in the GM by ID technology, we need many more parameters like ID, GM over ID, and GM by GDS, and many other parameters. So let us see where all these parameters. How can we find all these parameters? So let us go to Tools and Result Browser, and in the DC you can see there is in the DC you cannot see all these parameters because by default the cadence or spectra will not save all these DC parameters. So if we are explicitly saying the cadence to save all the parameters, it will not save the parameters. It will save only the DC operating point that you can see the all the parameters of this. Our MOSFET is M0. You can see our MOSFET is M0. And all these parameters, CGS, CDS, all this you can see, but this is only a single value. But we want all the values across the VGS. We sweep the VGS and we want GM and every other parameters for each value of VGS. But here we don't get it because by default, I repeat, by default, cadence will not store the operating point across the DC sweep. So we have to explicitly say cadence that we need all the points. For that, we have to write a small file. We have to create a small file, a small SCS file, .scs file, and say and ask the cadence to save the operating point. So let us do that. For that, create any file. And I'm creating a empty file, and I'm naming it as save underscore op. So you can give any name to this file. So the name of the file doesn't matter, but the extension should be .scs. So here is my file save op.scs, and open it. And inside that we have to we have to give the command to the cadence to save all the operating point. So I have to write save save. My MOSFET is M0. MOSFET is M0, and I want to save all the parameters uh, of M0. So let us save it, close it, and now we have to add this file to our ADE. You can add this file to anywhere you want. If you can add this file to your model library, or you can add the file to the simulation file. So it doesn't matter where you include. The only thing that does matter is you have to include this file somewhere, even in the model library or here itself you can uh, add. So I'm adding it in the definition file. So uh, save op.scs, this is my file. Open, and you can see that is saved in the definition file. Apply. Okay. Now run the simulation once again. And now check, you can go to tools, result browser, then you can check under the DC, we have all the parameters of the MOSFET M0. So it starts from M0 beta effective, M0 B effective, M0 beta effective, CBB, and everything, all the parameters is here. It is CGG is here, and where is GM? So this is GM. If you want to plot GM, just plot it, plot signal. So this is your how your GM varies with VGS, and you can see GM over ID also here. So you need not to explicitly calculate GM over ID. So it is already provided as a parameter in the simulator itself, and we will verify this by dividing GM by ID and plotting this directly from here GM over ID. So we got all the parameters here. We got all the parameters here just because we add that file and asked Cadence to save all these parameters. So if we didn't add those files, that operating point save op.ses, Cadence will not store these values. So if you want to plot all the DC parameters, so we have to load that file to ADEL, then only Cadence will save. So now we have all the parameters saved in Cadence, uh, and now we have to explicitly identify what are the parameters that we need to make all the GM over ID curves. So let us delete this, and first parameter I would like to add is the ID. So in the result browser, DC, and first parameter I would like to add is ID of M0. So I am sending this to calculator. So we got the expression here. I am bringing it here to the output. So here get expression. So this is our ID. Add. Similarly, I want the GM. So this is GM of M0. Sending to calculator and taking the output, get expression, and this is the GM. Add. So now let us plot them to make sure that they appeared here properly. You can see, let us save them. So this is the ID with respect to VGS, and this is the GM with respect to VGS for a particular W and L. And now we can let us manually calculate GM over ID. So we have GM here. So I'm copying the expression for the GM. Okay. And we have ID here. I am copying the expression for ID. And I'm editing this value to get GM over ID. So we have GM here, and I'm naming it as GM over ID 1. And GM already have the expression for GM, and let us divide it by the expression of ID. So ID, where expression for ID I copied earlier, so I can just paste it here. So now we got the expression for GM over ID, and just add this, and let us plot only the GM over ID 1. So the why I gave the GM over ID 1 is we already have we have GM over ID separately in the parameters list. So and we can compare that. We will come to that point. Now we got the curve for GM over ID. This curve we manually calculated by dividing GM by ID, but we saw same parameter here. GM over ID of M0 is given as a parameter directly here. So let us plot that also. Here it is GM over ID. So send to calculator, and I'm taking it to the output. Get expression GM over ID. So this is the GM over ID that we are getting directly from the simulator. So I'm adding that also. So let us plot these two and compare whether is there any difference between our manual calculation and the uh, direct parameter given by the simulator. So let's plot. So you can see they are the same. They are exactly the same. So we don't need both of them. So I'm deleting the first calculated GM over ID because we are getting this value, this parameter directly from here. So I'm deleting it. So we got ID, GM over ID. The next parameter we need FT, that is the transit frequency, and it is given as GM by CGG. GM by CGG will be in radian. So if you want that to be in hertz, like we have to divide it by 2 pi. So the expression for uh, transit frequency Ft will be Gm by 2 pi into Cgg. So let us make that expression here. For that we need Gm and divided by Cgg. So we already have the expression for Gm here. So I am copying it, and now we have to find Cgg. So in Cgg we can get from the parameter list. So you can see Gg is the total gate capacitance. Here it is the Cgg. So if you want, you can plot it, and I'm sending that to calculator to get the expression. So I got the Cgg here, and I'm pasting Gm value. So making the division. So now this is Gm by Cgg. So but we want the parameter in hertz. So we are adding a 2 pi here. 2 into 3.14, and let's see get expression and naming it as FT. And okay, let's plot it. Oh, there is something wrong here. I think we miss a bracket because yes, let's place the bracket here. I think now it is correct. So get expression, change, okay, let's plot. Yeah, now we got FT with respect to VGS, and let us move to the next parameter. Next parameter we need FT into GM over ID. FT into GM over ID is the next parameter that we are interested. So we already have GM over ID expression, so copy that. We already have FT expression also. So FT into GM over ID, and here I have to multiply. Here I have to multiply GM over ID with this. So I'm pasting the value and add. So let us plot this. So this is the curve of Ft into Gm over Id with respect to VGS. And the next parameter that we are interested is the overtime voltage, that is VOV. VOV given as VGS minus VTH. So let's see how can we make it. So let us go to the result browser, and the parameter VTH of M0 is given here. That is here is the VTH, and I want the expression in the calculator, so I got VTH over here, copied it, and VGS is here. So in the calculator I got VGS. Now I subtract VTH from here, and I'm taking that in the output. So that expression, so we got VGS minus VTH here, and naming it as VOV. Add. Okay, now let us test it. So it should plot VOV with respect to VGS. See, now we can see the VOV changes from near to 300 millivolt to minus 300 millivolt. It will be zero point 0.2 minus VTH plus 1 minus VTH to be near to 500 millivolt. So we can assume the threshold voltage is near to 500 millivolt. So that's why VGS minus VTH is following this curve. And so we got Gm over Id, transit frequency, Ft into Gm over Id, and VOV also we got. Now we need Gm by GDS. So GDS is also directly given here. You can see the GDS. So in the calculator, copy it. Let us take GM and divide it by GDS, paste GDS. So now we got GM by GDS, and I am taking that also here to the output. Get expression GM over GDS. Add. Okay. Now let's plot our new member, that is GM over GDS with respect to VGS. So this is the curve of GM by GDS with respect to VGS, and we need ID by W, that is ID by width. This is a little bit tricky because the width is given as a parameter here, or if we are not giving the width as a variable, we will be giving width directly here. So calculation of GM ID by W directly from cadence is difficult because we cannot do any mathematics with this value here. So I'm doing a little small trick here. I'm copying this voltage source, and to get the value of the width, I'm giving the same variable here. So don't misunderstand. I'm not using uh, I'm not using this voltage anywhere. I just want to get the value of width as a voltage just for the calculation. And it is not used for the simulation. It will be just used to calculate ID by W. To calculate ID by W, we need the information of W. So it is be easy for us to calculate if we get the information of W as a voltage or current. So I'm trying to get that as a voltage over here. So I name this as W. So So if I plot this W, it will be, the value will be equal to the width of the MOSFET. So there is no point of physical interpretation of the voltage because I'm not using that for simulation. I'm using only to get that value. So it is not at all related to the simulation of MOSFET. I just want to get the value of W. So basic, no connection. So it is not connected to anywhere. I hope you are not confused by this step because I want to get this 5 micro for my calculation. I cannot directly take the width as a parameter for the calculation. Cadence will not allow that. So I indirectly taking this 5 micro to my expression by just taking this voltage. So because I give the VDC as the DC voltage as the width, I will get W as same as 5 micro. So let us see whether I can do that. Let's run the simulation and result DC is W. So this W will be 5 micro. It will show us 5 microvolt, but we are interested in the value of 5 micro. 5 micrometer is what we interest in, what we want, but it is given 5 microvolt, but it doesn't matter. I just want the value of 5 micro. So now I can make IM. Now I can make ID by W because ID I already have. W I can take from here. So let us do that. I want to send this to calculator. So here it is, copy and let's plot ID. Here it is, and now I need ID by W. So let's modify this expression like ID by W, capital W, and let's divide this ID expression by the expression for W that we derived indirectly here. Let's add, okay, let's plot it. So now you can see the difference. This is ID by W and this is the ID. So we will interpret these plots later. Why we need all these parameters I didn't explain till now, but these are the typical plots people use in the GM over ID technique. So we are also making all the plots and we'll explain all these plots later. And now we got all the values of all the parameters that we need to make the GM over ID plots. And in all the plots here, we did the plot with the VGS as the x-axis and all the parameter in the y-axis. But in the GM over ID, we want all the plot to have GM over ID in the x-axis and the parameter in the y-axis. So that is not directly, that is not possible in ADEL. We have to do a little bit of Ocean scripting and all for this. And before going to that, we want to sweep the length from, we have 180 nanometer here and to 500 nanometer. It is and let us have a total step of, so let us have a linear step of 80 nanometer, so that we will get approximately 18 4 3, yeah, we will get four different values of length. So let us plot this, let us simulate this, and we can see all these parameters with different length. So our final target is to plot GM over ID curves with four different lengths. So now we got all the parameters, and but the only problem is now we can plot only with respect to VGS, but really we need all the plot with respect to GM over ID. So now we got all these values for different length, and I'm not going to interpret all these curves that we will do later. And the target of this tutorial is just to save the parameters for the for generating GM over ID curve. Now let us save this state, because we have all the parameters here. I saved the state, and saving this also. Save as mouse length. Okay, save. And this is all what we need for the NMOS. So for the NMOS, we saved all these parameters, and we will plot them in a next tutorial, because plotting is little bit different, and we have two different methods for plotting. We will show the plotting in Cadence, and we will show how to plot in MATLAB also. So those tutorials we will do separately. And now I want to, before finishing this tutorial, I want to characterize the PMOS also. So when I make the, so let us close this, and I think I saved this. Okay, and I will try to reuse all these expression, because everything will be the same, but only the direction will be different for the PMOS. So I will try to load this state and reuse most of these parameters. So I'm closing this and closing this also. And in the NMOS SCARA, I'm copying the same schematic to make the PMOS SCARA, so that we can save some time. Open it. First, delete the NMOS, and we have to insert the PMOS here. So let us insert the PMOS. I have my PMOS here. So I have my PMOS here. So the VDS is same. So we can connect this like this, and the bulk is connected to the VDS. Bulk is connected to the drain, and we have to change the VGS connection from here to here. So if we want to use our previous state and all the previous expressions, we should not change name of any parameter, because here earlier we had a MOSFET name M0. So here also we are using the same M0. But if we are using here some different name, like suppose if we are using the M1 here, then again you have to open the save op.scs file that we did here, this save op.scs. So if we ask the Cadence to save only the value of parameters of M0 here. So if your MOSFET is different and your MOSFET name is MN0 or MN1 or something, then you have to change here also. Or if you want to save more than one MOSFET, then you have to add save MN0. Suppose your next MOSFET is MP1 or MP0. So whatever the MOSFET name that you have here, that you have to mention here. So for our case, we are reusing. I want to reuse all the files, so I don't want to change anything. So I'm keeping this also as M0, and the only difference is uh, initially this was V1 earlier, and but when I copied it became V3. So I'm lazy. I want to reuse it again, so I just named as that also V1, and the length and width, or the width and length and th is PMOS, pilot, save, and launch ATE. So as I explained earlier, I want to reuse the same state so that I can save some time. Okay, everything will remain the same except the sign. So by doing this, let us make sure that the file is there, that save underscore op dot scs file is there, so that Cadence will save all the operating point, and my DC chip is here and the value is V1, and that is the same value that I have here for the VGS. So everything is fine. So just run the simulation, and let's run. Let's see the plots one by one. So cancel. So let's plot ID. So the ID is as we expect, but the only difference is now the sign is negative. So that's why the curve is going like this. Really speaking, when the VGS increases, the current is increasing, but in the opposite direction, that is the negative direction. But it is not so easy to see. We are not familiar with the negative curves. We want everything to be positive so that we can easily interpret. So I'm just adding a negative sign here so that we will get a positive current. Change. Okay, let's plot it. Now it is easy to analyze even whether it's a PMOS. When we increase its VGS, its current will increase. So let us change the everything whichever is coming negative, we will change its direction so that it is easy for us to visualize and analyze. I don't think GM we need to have any change. We need not change GM, it is the same. And GM over ID also will be same. Oh, okay. GM over ID. Okay, let's plot it. It's also the same, so we need not change it. And FT. FT also not negative. And FT into GM over ID also fine. And VOV we may have to change, because VOV, really speaking, if we are taking the modulus of VGS and VTH, VOV should start from negative and end it in a positive value. Here we are getting just opposite, that we are getting VOV starting from positive and then going to negative. So let us add a negative sign over there also, so that we can easily interpret the curves. Okay, so we got the VOV as similar to the NMOS, so which is familiar to us. So GM by GDS, I don't think we need to change anything. Let's go, yeah, we are fine. And ID by W we have to change. It's the same as the ID. So just add a negative symbol here. Yeah. change. Okay. So now we got all the parameters for plotting the GMO ID curves for the PMOS also. For the PMOS, also we will find all these parameters for with different length. And why we are not sweeping width is when we analyze the GM over ID curve, all of the parameters will be almost independent of the width. So that's why we are not sweeping the width. So this also we can load this. We have already a saved state of here, so we can load this and let's run. Now we got all the parameters that is required for this to generate the GM over ID curves. We have GM over ID, FT into GM over ID, VOV and all. But the only problem is in the x-axis we have VGS now. But in all the GM over ID curve, we need x-axis as GM over ID, and in the y-axis we want different parameters. So we will do that in the coming tutorial. In the next tutorial, we will see how we can plot this in Cadence itself using the help of Ocean script. It is not difficult, but we need to have simple. We have to add some simple steps in the Ocean script to get all these beautiful curves in the Cadence itself. But it will be helpful if you don't know the MATLAB, or if you are not familiar with MATLAB and you want, or you don't have the license of MATLAB and you want to plot the curves in Cadence itself, then you can use it. But in case you are very familiar with MATLAB and you want to play with all the data, then it is better you plot, you save all these files in all this information to a file and access the file in the MATLAB and plot whatever you want. So in this tutorial, we will explain, we will illustrate, we will show both of the method. Uh, First, we will plot in Cadence, and in the next tutorial, we will plot that in MATLAB.